Hi, guys. Welcome to the presentation. Um, I'm going to move through stuff fairly quick. We've got some ground to cover, so I'm going to dive right in. So we're talking about industrial chillers today. So a package chiller is a heat transfer device, specifically a water to air heat transfer device, and moves heat from point A and deposits it at point B. A chiller absorbs heat from water or glycol, and by utilizing a refrigeration system, rejects that heat into the air or another medium. In the diagram, you're seeing what's basically, it could be a tank of cutting oil, it could be a tank of hydraulic oil, or it could be acid bath. And what we're doing there is we're immersion cooling. So basically, we've put multiple plates heat exchanger into the tank, and then we're pumping cold glycol through those plates, absorbing the heat, pulling the heat from the tank, and rejecting it at the chiller. So utilizing a vapor compression refrigeration system, the chiller utilizes an internal heat exchanger or evaporator to quickly absorb heat from the incoming water glycol solution and return a cool stream of water back to the process to be heated again in a constant cycle of heat exchange. Chilled water is defined typically as below ambient or below the temperature of the surrounding air, often below 85 to 90 F temperature. When encountering chillers in the field, it is important to understand the water temperature required to cool the process. It is important at that point to make a decision. Is chilled water really required here? What are the options outside of a chilled water system? When trying to understand chillers, it's important to understand what is not a chiller. Fluid coolers, dry coolers. There's no refrigeration. Basically, fans with glycol coils, no ability to drop the temperature below the ambient. And there's cooling towers. Also, we call these coolers, not chillers. Chillers, and they're used for cooling solutions at ambient temperature or very high temperature for certain processes. Now, with a water spray type setup, you can get lower than ambient and reject more heat. So, depending on the cooler, but these are not chillers, these are coolers. So, different types of chillers: air cooled with axial fans, external and internal installation. So, when I say axial fan, I mean a propeller style fan. Um, uh, Thing to note with propeller style fans is they cannot be ducted. I know they often do get ducted, but they should not. Whenever you're doing duct work, you should be using a centrifugal fan. And you can, as shown there, that's a type of chiller, air cooled with centrifugal, and that has a blower type on it, so you can actually handle static pressure of the ductwork. Then there's water cooled internal chillers. We'll see a lot of these in larger plants. The general rule is water cooled chillers are more efficient than air cooled chillers, but often the higher capital costs can force people to buy an air cooled chiller as well. Water cooled larger chillers with screw compressors and internal installation, those are typically going to be hooked up to a fluid cooler to cool the condensers, as opposed to using airflow over the condensers that you would find in an air-cooled chiller. Then, of course, we have the big boys, water-cooled centrifugal and magnetic bearing chillers. You often find these in the comfort cooling market, but also large industrial plants. And these are basically water-cooled as well. They will be typically the chiller be mounted and then hooked up to a cooling tower to provide cooling for a multi-story building. And then you can also have the heating side run off that on the HVAC side. Something you'll see a lot of, the warmer the ambient gets, the more people are not going to put chillers indoors. They're going to want to reject the heat outdoors. So what I'm showing there is a split system chiller with a remote refrigerant condenser. So basically, the only portion of the refrigeration system that is outside is the condenser and the fans. So the fans blow air over, and then the refrigeration piping is piped inside the building to the compressor and the evaporator and the control system. So chillers are used in lots of different applications, process and comfort cooling. So typically process cooling is often a dynamic load based on a manufacturing rate. Supply water temperature can be 15F to 75F. Chiller runs in the winter or in free cooling mode. And comfort cooling is typically non-dynamic. We're dealing with return air and a consistent temperature. The load is pretty consistent. It changes somewhat over the day, but not like you would see in process cooling. Typically 45F supply, 55F return. Exception would be if we were doing outdoor air tempering or discharge air control, makeup air, where we have to cool changing ambient temperatures down to a certain set point inside the building. So right there we have a comfort cooled. You have an air cooled chiller hooked up to multiple air handlers on each floor, and these are providing cooling to the cooling coils in those air handlers. And we have process cooling. So this is, a kind of a standard you'll see in the industrial side is an open tank of coolant, whether it be water or glycol, hooked up to a chiller, which is basically just keeping that temperature cold in the tank while the process pump distributes all around the building. So all the loads in the on the shop floor. Process and comfort cooling chillers can often be interchanged. However, if you require tight control of temperature or have variable or multiple loads, then a process package chiller is the wise choice in most cases. I'm not going to spend a lot of time on this. You don't have to understand refrigeration to understand how to apply a chiller in the field. It certainly helps, but it's kind of a package solution. So, but typical basic refrigeration system, we have you call these opposites. So we have the compressor, which compresses refrigerant, the expansion valve, which expands refrigerant, and we have the evaporator, which is going to cool either air or water, and then you have your condenser, which is going to reject the heat. Graphically, basic refrigeration cycle is here. Right here, you have the curve for the refrigerant with your liquid to gas vapor line over here. And all refrigeration systems, except absorption, operate on this principle. So basically expansion, evaporating, compressor, condensing in a constant cycle, which rejects heat. In refrigeration, really what we're doing is we're taking advantage of the changes in pressure caused by condensing and volume and how that affects the boiling points of that refrigerant. By changing pressure, adding heat, taking away heat, we change the state. And that allows us to move heat around. So the evaporator or cooler absorbs the heat from the water, thus cooling it. We absorb heat by evaporating the refrigerant or forcing it to change from low pressure liquid to low pressure gas. Heat naturally flows from hot to cold, and the greater that temperature difference, the higher the rate of heat transfer. There's different types of evaporators depending on the type of chiller you see, but they all accomplish the same thing, which is to absorb heat and change the phase of the refrigerant. The compressor compresses or reduces the volume of refrigerant gas. By reducing the volume, you increase the pressure of the gas, thus changing the heat transfer properties, boiling points, and condensation points. The air-cooled condenser rejects heat from the refrigerant by taking high pressure, high temperature refrigerant gas and cooling it. We are left with a high pressure, low temp liquid refrigerant. This could also be replaced with a water cooled condenser, which would accomplish the same thing. So basically a condenser coil would be constructed very similar to what you would see in an automobile radiator. So tubes and fins, get as much surface area as we can so we can dissipate that heat from the refrigerant and reject the heat from the process. The TXV or expansion device is the opposite of the compressor. It increases the volume and reduces the pressure of refrigerant. It is located just before the evaporator. Of course, the condenser fan will move airflow over the condenser to get maximum heat dissipation off the coil. As ambient temperatures change, especially northern US, Canada, uh, we have to slow those fans down because we don't need as much air. So to operate in winter conditions, we need to slow those fans down and keep the pressures balanced in the system. And of course, a package chiller would have a microprocessor controller. So basically, this would be mounted on the control panel, regulates evaporator, water outlet temperature, turns pumps on and off, gives you error codes. So basically, the brains of the operation. So if I put both, the graphical illustration and the practical, you can see how the different components go around the system. So in the bottom here, so any like air conditioning, even your refrigerator at home operates on these principles. What we're doing in the chillers, we're now adding a pump that we're going to take water and put through our evaporator right here to cool the glycol for the system. I'm just going to have a glass of water here, guys. So this is an important, and if you could get one takeaway today, would be understanding open loop versus closed loop systems. So what you're looking at there now, this would be a non-pressurized reservoir. So basically, external to the chiller, it is open to atmosphere. That makes it an open loop. And in terms of when often if you call someone to select a chiller, have questions about chillers, the first question they're going to ask. So this one would be open because it's open to atmosphere. And when this one is a closed loop. So closed loop means nothing's going in and nothing's leaving, only heat. So basically on the water side, we have the pump, but because it's not open to atmosphere, we need to have an expansion tank that's going to expand as the water heats and contracts, an air eliminator, and a pressurized buffer tank. So this would be what I would consider a closed loop, external closed loop. So we're talking package chiller components. I'm bringing up just a cutaway of a standard small chiller. And the idea of these chillers is to provide a package solution in the box. So you can see in there that we have the buffer tank, we have the expansion tank, we have the pump, the compressor, the microprocessor, the condenser fan. Whole idea of this is to hook up your glycol or water connections and your electricity, fill the system and the external loop, and set your temperature, and then we start up the chiller. A very simple, all-in-one solution. But a lot of chillers out there, you're going to find that they're custom, but they all have the same components. So let's keep talking about what I said was probably the most important thing is understanding the plumbing side of the chiller, the fluid mechanics of the chiller. I'll just bring up these slides. So in a pressurized tank chiller is going to be used when the plant will remain closed and there's no need of filling it. That's a benefit. When you have an atmospheric tank like you have here, and an open tank chiller, you're going to have loss of glycol and water to evaporation. So you need to have somewhere to go. We'll talk a little more about open and why you would use an open later. But important thing to remember is a lot of systems out there, they have an existing tank they want to cool. They want to integrate a chiller to an existing tank. With a closed loop, you can hook up a tank and not lose any water. But if you put an open tank like this, the water is going to flow down and overflow the tank. Very important. It's a very common problem I see out there when someone gets a new chiller and they did not understand the fluid mechanics involved. So this is my opinion, but closed hydraulic circuit is always preferred on a permanent installation. So if you have an outdoor chiller that's permanent, um, basically we want to use a closed loop pressurized. We want to seal that system up and operate it so no contaminants get in there. There's no rusting. It's a lot much better, plus better pump performance as well. So in a hydraulic circuit with an atmospheric conversion kit, so we make this tank a conversion. So this is now open to atmosphere. This is non-pressurized. So the advantage with non-pressurized is when you shut off the pump to the chiller, there's no standing pressure in the line. So if we think about the plastics industry, where they'll take a portable chiller and move it from load to load, uh, you have to be able to disconnect those pipes without losing water. So there is an advantage there, and a lot of plastics industries want that.
We had someone pop into the chat and say hydraulic or hydronic.
It depends what you look at. Hydronic is probably the way we say it here, but it's also, you can use the term hydraulic as well.
Great, thanks.
So the most important industry is the plastics industry. That has been I would say 50% of my business is plastics industry. So that should be an industry that you'll see a lot of chillers. As you see in this one, they have a bunch of injection molders. They have a chiller that's going to cool the mold temperature so that we get a good release of the plastic. And then they put their hydraulics. So I'm talking oil hydraulics, not water hydraulics, are going to be cooled by a cooling tower just because they can get away with a much higher temperature. And the chiller is more precision for the mold. Welding industry is probably my number two. Spot welders, resistance welding, laser welding, robotic welding cells are extremely popular right now. We do chillers for cells that have multiple welders. And the idea with cooling welders is we maintain the integrity of the tips. The tips don't burn up by putting through a circulation of chilled water. Other uses: pharmaceutical industry, food production, printing industry, chemical industry, hydraulics, compressed air, biogas, you name it. There's every week I find a new industry, it seems. So let's talk about some not we talked about I want to talk about some non-standard applications because that's what you're going to see out there. If you see here, this has been ducted. Now this chiller here has a very specific axial fan that can handle external static pressure, so it can be ducted. So there will be a lot of requirement to duct. I see a lot of it in North, just because they want to keep the heat in the building sometimes, and sometimes they want to reject it in the summer but keep it in the winter. Multiple loads with a portable chiller. We briefly talked about that. I have a portable chiller there on wheels. That's a 20-ton chiller. And a lot of plastic plants, depending on their orders, might be running different lines. And instead of buying a huge system, they will use a portable chiller to bring around and rehook it up because it's non-pressurized. So special working conditions. So right here I have would be an air compressor being cooled by a chiller. Most air compressors can be cooled using a fluid cooler. But depending on the situation, what type of compressor, we have done quite a few with chillers as well. And with these, we often put a bypass valve here, and we have to size for the flow that's required for the air compressor. A lot of older air compressors were sized really for city water, and they didn't care what the leaving water temperature was. So with a chiller, I do care what the leaving water temperature is because it cannot be more than 87 Fahrenheit coming back. So I must put a mixing valve here to balance the system. So that's how we do it. We size it from the air compressor back, make sure we get the proper flow and the proper temperature across the air compressor. disconnected hydraulic circuits. Here's this diagram again. So basically,
We have one question that popped through real quick. What
Sure.
limits us to 87 degrees?
So the refrigeration system, most refrigeration or packaged products do not want a higher return water temperature coming back to 87F because it'll overheat the evaporator and it'll cause problems in the refrigeration system. So as a general rule, I pushed it up to 90F on certain, depends on the flow variable. But typically anything over, if you're in those temperatures, you should be using a fluid cooler anyway.
Great, thank you.
So disconnected hydraulic circuit. This is obtained by placing a tank between the chiller and the user. This allows the user to be provided with water flows and available pressure and may be incompatible with the proper operation of the chiller. If you would think in this case that this chiller has a primary pump that's pumping from the tank and back to the tank, maintaining the tank, this would be considered a process pump. And so basically this may need a very high pressure depending on, we may be going all the way across a plant, but this allows a constant feed of cool water to this pump to distribute throughout the plant. Bubble pump, so redundant pump. We do get a lot of requests for this. People want a secondary pump that will share the load as well as a backup in case the other pump fails, the other one comes on. I see this a lot in biogas where they don't want any overheating of the condenser. So oil cooling, hydraulic oil cooling, so cutting machine tools. So basically we can put a chiller, have a oil heat exchanger here and cool the oil as it comes in, comes out. That's one that we've done here. It's a pretty quick fix for, maybe places where hydraulic oil or cutting oils need to stay within a certain tolerance. So in cutting oils, if the cutting oil gets above a certain temperature, it starts to affect the specs of the actual part that you're machining. So this is a nice little application. I see quite a bit of it in the field. Compressed air to water after cooler. We see quite a bit of that. So compressed air, instead of using a propeller type after cooler, we're using a water cooled. This provides better control, and in certain applications, better heat dissipation. Multiple loads on one chiller. So say we have a small chiller with multiple small loads, it may be a laboratory. We always want to have a balancing valve at each branch so that each is getting the right amount of flow. And I've done up to 30, 40 loads on one chiller, as long as the piping is correct. A lot of small chillers will have what's called a bypass valve, which allows you to balance the flow through this system as well. So you would put that would actually be internal in this machine, but would be externally, it would be here. Very common, cooling using a remote heat exchanger, many applications. So basically we have a package chiller here that's pumping chilled water to a heat exchanger in a constant loop. And then we have, in this case, we were doing city water. So city water was too hot for a food application.
We have one more question here.
Sure.
Why is the balancing valve on the supply side? Maybe in the diagram.
Going back. Yeah, so typically, the balancing valve. So basically we want to this is an open tank system. So we're going to balance this flow. So we need the furthest one out needs to have, the closest one in needs to have some valve turn so that we can force water to the furthest low. If water will always take the path of least resistance. So unless you create resistance at the first, you won't get the proper flow at the last. So going back to cooling using a remote heat exchanger. So this one we were using city water I believe it was they were making dough. The water had to be at a certain temperature. So basically what we did was put a food grade heat exchanger, put food grade glycol on one side, and cooled that city water to the correct set point, which I believe was about 4 or 5 Celsius. Indirect batch cooling using immersion cooling. So you could have an existing tank. We can run some copper or stainless steel pipe and then run some chilled glycol through here to basically run this tank down to temperature for, could be a batch of anything, pharmaceuticals. I've done this one. So it it really depends on the situation, but immersion cooling is a very nice use of a small package chiller. So ducting, this is fairly common up north. We see right here that they've ducted it, and they've also allowed a basic operable louver that can direct that heat either out of the building or into the space, depending on the season. So this is also used in air compressors as well. What I'm looking at here, this wasn't my chiller, but the ductwork is attached to the unit. If you see my diagram, you should never attach the ductwork to the unit if it's a propeller fan. If it's a propeller, if it's a blower style centrifugal fan, you could attach. So basically, if it's going to be, we call this a standoff, and basically we can't use propeller fans to pressurize a duct plenum. This is one that we'll see quite often, is where they don't really have much space. The chiller's tucked away. You can order certain chillers that can only take the air from one side as opposed to both sides. So that's where we have restricted clearances, and a chiller can be built to operate in a very small space like that. Right here we have a chiller which is operating in low ambient. So obviously northern US down to mid US. What you see there, those in the summer, those would be a expanded panel right there. Those are called winter panels, and they reduce the air going across. And also we're slowing down these fans with temperature. One thing we're seeing a lot more of these days is a free cooling system. So the free cooling equipment allows to supply completely or partially the cooling capacity normally provided by the refrigeration cycle in the correct season. So we talked about dry coolers, we talked about chillers. Well, this is both. So this one can do either. Once again, northern US, you could take advantage of the cold winter ambience to cool your glycol instead of running mechanical refrigeration. Obviously, the savings on electricity in that case would be huge. Let's talk about basic sizing. Resist the urge to oversize. 70% of units are oversized in industry, leading to premature failure of compressors and fans and erratic cycling with poor control of temperature. Size for the geographic location and ambient temperatures. A 20-ton chiller in Minnesota is not a 20-ton chiller in Houston. What are the winter conditions on outdoor units? Do I need glycol antifreeze? What percentage? The lower the leaving water glycol set point, the more energy is required to accomplish the required capacity, and vice versa. Many specifications on older equipment are based on city water, where you do not care about leaving water temperature. It's important to understand the relationship between flow rate, temperature rise, and required temperature set point. The equation we live by on the chiller side is 500 times GPM times the temperature difference in Fahrenheit. It's derived from the specific heat equation. So an example would be an injection molder needs to be cooled. The machine spec requires cooling water 50 degree F and a flow rate of 50 GPM. The water leaving the molder is estimated to be 65 degree F. So if we plug all that in there, 500 times 50 GPM times a 15 degree temperature difference, we come out with 375,000 BTUs. 1 ton of cooling is 12,000 BTUs. That means we need 31.25 tons of cooling required. Now, you'll find out in industry with existing equipment, getting that information isn't always that easy. So it's on a new job, it's not a problem. Usually there's a specification you can look at. So when I talked about process chillers, I always, if it's going to be dynamic load, I typically try to use multiple compressors. This gives me the ability to turn down the chiller and not cycle compressors as much as you would with, say, a single compressor unit. So process cooling, based because of the dynamic nature, is better to have more compressors. As I just mentioned, the more compressors, the better.
We have one more question here.
Sure.
How do you decide the percentage of glycol in cooling water?
Okay, so the percentage of glycol required typically is going to be what your winter ambient is. So basically, there is a graph. I don't have it with me, but there's a graphical illustration. But typically, we play it safe. If I was in the northern U.S., I'd be at 40% glycol. If I was in Alaska, I'd be at 55%. So the ambient temperature is really what sets the glycol percentage you need. The other thing to consider is if it's a closed system or an open system. If it's a closed system, because that system's pressurized, the freezing point is a little different. If it's an open system, then you need a little higher percentage of glycol than you would in a closed system. Lastly, here I want to talk about the microbrewery applications. This is very, very common we see a lot of microbreweries pointing out. Most of them have a package chiller, and typically in brewery applications, we're going to want about 25F. So typically we're using subcooled glycol, so below the freezing point, and very common. A lot of chillers being sold in the USA for microbrewery applications as well as Canada. Typical brewery right here, you see you have a packaged glycol chiller, jacketed tanks, fermentation tanks, conditioning tanks. These are all jacketed stainless steel tanks. The glycol sits in the outside of the jacket. We could also do some refrigeration for the cooling room, as well as the wort chillers. And sizing a glycol chiller, that's something probably where you want to talk to a technical person to figure that out. There's a lot of rules of thumb out there, but my feeling is that they can lead people into an undersized or oversized chiller.